Hi, I'm Austin Clements, the tech lead on the Go runtime and compiler, and I'm going to be telling you about a recent improvement we made to the Go runtime to support loop preemption. Since we released Go 1.5 5 years ago, with a concurrent garbage collector, I've been on a quest to squash every remaining source of garbage collector-induced latency. We've made huge strides applying everything from novel garbage collection algorithms to good old engineering to drive stop-the-world latency lower and lower. Finally, for a long time, we were stuck on one last problem, and it almost seemed silly compared to the rest. Tight loops. So, what's the problem with tight loops? Well, the garbage collector really only needs to stop the world for a fraction of a millisecond, but in order to do that, it first has to get the attention of every Go routine. Sometimes this is easy, because a Go routine voluntarily gives up control by waiting for something. But if a Go routine doesn't block on its own, say it's doing some large computational task, then it's not so easy. In this case, the Go runtime needs to preempt the running Go routine so the garbage collector can take control. And this isn't just about garbage collection. Preemption is one of the keys to how Go can scale to a huge number of Go routines while using only a small number of threads. Go 1.0, in fact, only supported voluntary preemption. If your Go routines weren't blocking on their own, too bad. Since Go 1.2, however, we've relied on function call preemption, where every function call checks if there's a pending request to preempt that Go routine. In fact, most Go functions already have to start with a check to see if they need to grow the stack. So we make that exact same check also see if there's a preemption request. Either way, it calls into the runtime and the runtime does the appropriate thing. What's neat is that we actually get this for free because we can make that single check in the code do double duty. Honestly, this served us well for a pretty long time, but it has some definite problems. Usually, calls are happening constantly, but it's certainly possible to go for a long time without making a call. For example, long computational loops without any calls can delay preemption. Now, what I've got on this slide is a bit of a silly example, but here's a real-world example from a bug report from Twitch. This is an HTTP server running on 48 cores. Time goes from left to right, and you can see tons of activity across a whole bunch of CPUs, except that there's sort of this steady drumbeat where the system grinds to an almost complete halt for about 5 milliseconds at a time. Now, the fact that there's still a little bit of activity in these windows is actually key to this bug. In each of these windows, the garbage collector is trying to stop the world. It immediately preempts almost all of the Go routines, but each time there are just a few Go routines that refuse to stop. And when you dig into this, it turns out that these Go routines are doing large base64 decode operations. And it turns out that is a tight call-free loop. And you'd never guess, because it's buried down in the implementation of the standard library. Now, what's fascinating about this example is that this isn't just a latency problem anymore. We have 47 CPUs doing nothing while we try to preempt this one last Go routine. This is a 47x throughput problem. So we have a latency problem, a throughput problem, and it turns out, in really rare cases, a deadlock problem. Unbounded call-free loops could deadlock the Go scheduler. This little example on the slide even looks like you're making a call, but atomic load is actually compiler intrinsic, not a function call at all, so there's no preemption check here. Now, you may say you should never write a spin loop like that, and you'd probably be right, but it's not always obvious that this is what's happening. This is some real production code, only slightly paraphrased. Now, this isn't great code, but not all code is. And it certainly doesn't look like dangerous code. And actually, it even worked fine for a long time, because after all, it has calls in it. Until it no longer had calls in it. In Go 1.13, we tweaked the lock implementation so the compiler could inline the fast paths, rlock and runlock. Then the compiler turned the code into this. Now we have a problem. If the lock is uncontended, we can go around this loop without making any calls and without doing any preemption checks. And if the goroutine that's supposed to set c.flush and get us out of this loop can't run because the scheduler can't preempt this goroutine, then this will deadlock. This is obviously bad, but what's worse is that a change in the sync package introduced a scheduler deadlock into existing application code. This tells us that function call preemption is actually not robust. All this led to some rather unfortunate conventional wisdom that if you have a long-running call-free loop, you should add a call to runtime.gosched into it in order to force the preemption. Every time I saw this, I shed a tear. It meant we were exposing users to unfortunate and complicated implementation limits of the runtime. This is not a good user experience. Despite all the examples I just showed you, function call preemption honestly worked pretty well the vast majority of the time, but it also certainly had some definite problems. Tight loops delayed preemption, which caused scheduling latency. This latency could cascade into application-level throughput problems, and in the worst cases, loops could even cause scheduler deadlocks. While these problems were rare, when they did happen, they were really difficult to diagnose. And even if you could diagnose the problem, you may not be able to fix it if the loop is in code that you don't own. We needed a way to preempt tight loops. And in Go 1.14, we finally landed a solution to this that we call asynchronous preemption. Asynchronous preemption bounds preemption delay to about 25 microseconds, even for tight loops, with zero performance overhead to your code and only about a 0.3% increase in binary size for additional runtime metadata. And it eliminates the need for the unfortunate gosched workaround. But before I tell you how it works, I want to first tell you some of the things we tried that didn't work. As often happens, Go defied standard solutions to this problem, but we learned a lot from trying them. Attempt number 1. Lots of other languages preempt on back edges. Let's just do that. Anywhere the code jumps backwards in a loop, compile in a preemption check, actually a lot like the one at function entry. This one's a little more complicated than function entry. We're in the middle of a function, so it's sort of juggling all of this state, local variables, reordered operations, etc. If there's a preemption request, the function has to first kind of put down all the balls that it has in the air before it can call into the runtime. We didn't need to do this at function entry because it hadn't started juggling anything at that point. We implemented this, and actually, it works great. It also slowed down benchmarks by an average of 8%, even when there was no preemption happening. Basically, CPUs love tight loops, and we just made every loop loose. We tried lots of tricks, and were able to improve on this a little, but never to an acceptable point, especially for the worst-case benchmarks. From this, we learned that adding instructions to loops simply isn't a viable option for Go. Now, we're going to have to pay some cost when we are actively preempting a Go routine, but here we're paying for the mere possibility of preemption all the time. We really want a zero-cost solution. So here's a crazy idea. Can we branch without a branch? We hardly ever take this branch. Can we sort of conjure it into existence only when we actually need it? Yeah, actually it turns out you can. There's another technique some languages use called forward simulation. The idea is that the runtime breaks into the Go routine wherever it is, basically the way a debugger would. Then it single steps through the code, again, very much like you would in a debugger, until it reaches the backwards branch. At that point, the runtime says, actually, don't go that way, jump over here instead, to go over to the preemption path. There are a couple of ways of implementing this. The usual way, and the reason it's called forward simulation, is to actually implement a machine code interpreter that can do this single stepping operation. But the Intel x86 manual is 5,000 pages long, and I really didn't want to implement an interpreter for that in the runtime, along with interpreters for 8 other architectures. And I don't think you wanted to carry that around in all of your Go binaries either. But there's already a fantastic machine code interpreter for your CPU. It's called your CPU. And CPUs have built-in support for single-stepping in order to support debuggers. And it turns out that a program can single-step itself. I honestly wasn't sure that would work until I tried it, and it turns out it does. So we can do this without implementing a whole machine code interpreter. And this approach works great too, until you attach an actual debugger. Then the debugger gets thoroughly, deeply confused because it can't tell the difference between a program single-stepping itself and someone using the debugger to single-step the program. So this was a lot of fun, but ultimately kind of a dead end. We did learn a few things from this attempt, though. Keep it simple, and consider the end-to-end user experience. Don't confuse the poor debugger. Let's turn to a different source of inspiration. Operating system kernels preempt threads all the time, and they don't need these preemption checks all over the place, or interpreters, or single-stepping, or anything like that. OSs do this using hardware interrupts. That's not something we can use in user code, but we can use signals, which are basically the user space equivalent of interrupts. Now, Go's OS/signal package won't let you do stuff like this, but at the runtime level, a signal lets us stop a goroutine that's running on a thread, save its CPU state, basically taking a snapshot of the state that it's juggling right now, swap another goroutine CPU state onto that thread, like, say, for a garbage collection goroutine, and resume running on that new goroutine. This works great for an operating system, but there's a problem in Go. The OS doesn't have a garbage collector, but we do, and the garbage collector needs to know exactly where all of the pointers are in the stopped Go routine. But we stopped on some random machine instruction while it's juggling all this state in the air. Who knows what is or isn't a pointer here? And we already dismissed forward interpretation as a way to get us into a known state. So signals give us an approach that's zero overhead for regular execution. But now we need to make it work with the garbage collector. But wait, you may be wondering, how does the garbage collector normally find a goroutines pointers? It may be fairly obvious when you're looking at Go code what is and isn't a pointer. You just sort of look at the types of different variables and so forth. But the runtime only gets to see the compiled code and a big blob of bytes that are the goroutines stack. So the compiler produces what are called stack maps. These tell the runtime exactly which stack bytes are pointers at every call site. And we only needed the stack maps at call sites because that was the only place the garbage collector could stop a Go routine before. And that brings us to our fourth idea. Use signals and just have GC stack maps everywhere, at every single instruction a signal could possibly stop a Go routine at. This also actually basically works. But one, this is a huge amount of metadata. It makes every Go binary about 10% bigger. And two, it's basically impossible to test. If this metadata is even slightly wrong in just a few places, it would cause bugs that are utterly impossible to diagnose or reproduce. So this idea of using signals is good, but we need some other way to find pointers. So keep it simple and consider the end-to-end user experience. For example, avoid things that confuse other tools. Adding explicit preemption checks to loops is probably the simplest approach, but turns out to be too costly for Go code. Signals, on the other hand, have zero ongoing cost, but can stop the code anywhere, so they're only half of the answer. The garbage collector needs some way to find pointers where we stopped. But just having stack maps everywhere bloats binaries, and it turns out doesn't actually keep it simple. And this brings us to the solution we landed on in Go 1.14. Signal-based preemption with conservative innermost frame scanning. We're going to solve this problem by sprinkling in just a tiny bit of a different type of garbage collector. One of the many dimensions on which you can classify a garbage collector is whether it's precise or conservative. Go's garbage collector is precise. It has lots of metadata that tells it exactly what is and isn't a pointer. A conservative garbage collector, on the other hand, just looks at bytes in memory, and if something could be a pointer, it assumes it is a pointer. If it looks like a pointer and quacks like a pointer, it's a pointer. Conservative garbage collection only works if the garbage collector is also a non-moving garbage collector. Most GCs are moving garbage collectors, meaning that they can move objects, so they have to be able to update pointers to those objects when they move them, which means they really need to know what is and isn't a pointer, lest they corrupt memory by adjusting something that looked like a pointer but actually wasn't. But conveniently, and rather unusually, Go has a non-moving garbage collector, so it's compatible with conservative garbage collection. Now, conservative GC generally has some downsides relative to precise GC. There's a reason that we made Go's garbage collector precise, after all. But conservative GC has a key property. It doesn't need stack maps. And stack maps were exactly our problem. So, send a signal to the goroutine to stop it. It'll stop in the middle of some function, and we can examine its state. Probably it stops somewhere that doesn't have a precise stack map, but that's okay, because we can conservatively scan the function's state, and just assume that anything in the function state that looks like a pointer is a pointer. And we only have to do this for the innermost frame, the function that we stopped in. We can precisely scan the whole rest of the goroutine stack, because all other functions on the stack will be at calls, so we have precise stack maps for all of their stack frames. Now, this is not without its own limitations. Something any solution has to deal with is called an unsafe point. These are places where it's simply not safe to preempt a function. For example, it's not safe to preempt a function in the middle of manipulating an unsafe pointer. If the signal does land at an unsafe point, we handle it by simply waiting a moment and retrying the signal, which works but can delay preemption, especially if this happens repeatedly. Also, the whole runtime is actually a giant unsafe point right now. This is mostly harmless because the runtime mostly doesn't have tight loops, except during memory zeroing and copying. This is something we intend to fix but haven't gotten to yet. Now, the good news is the vast majority of the time, these limitations are pretty minor and much better than what we had before. Now, I wanted to share some bits of the implementation of this because if there's one theme of this work, it's that it's full of surprises, and the implementation was no different. If you've worked with Unix signals at all, you're probably familiar with sigkill or perhaps sigint, which stops a program when Control-C is pressed. There are a whole bunch of signals. The problem is they all already have assigned meanings, none of which are preempted goroutine. So we have to choose carefully. We chose sig-erg. Even if you're familiar with signals, this is decidedly in weird signal territory. It indicates an urgent condition on a socket. There are several reasons we chose this signal. For one, it's basically useless. Approximately no one uses, or for that matter, knows what an urgent condition on a socket is, and even if they do, they're probably still not using sig-erg. But that alone isn't reason enough. It's also safe to receive spurious sig-ergs, and for multiple sig-ergs to be coalesced, because it only tells an application that it needs to go and check all of its sockets for this urgent condition. So, on the off chance that an application is actually using sig-erg for its intended purpose, our use won't interfere with the application. And finally, since most signals indicate something is wrong, debuggers will stop on most of them. But sig-erg is one of the few signals that they won't stop for, because it's more of a heads-up signal than a something's wrong signal. So we send a sig-erg to the thread running the goroutine that we want to stop. When you're doing low-level signals programming, like in the runtime, this kicks the thread into a signal handler. The main thing you need to know about signal handlers is that they're really hard to write. The thread could have been interrupted anywhere, It could be in the middle of the memory allocator. It could be holding arbitrary locks. Because it could be doing anything, there's almost nothing we can safely do in the signal handler itself. I spent a long time trying to implement the whole preemption mechanism in the signal handler itself and driving myself nuts in the process. Then, Jerry helpfully suggested I should just get out of the signal handler, which was a fantastic idea. So now, the signal handler just checks if it's safe to preempt the goroutine, and if so, it simulates that goroutine calling into the runtime and returns. This, in turn, resumes the goroutine. Now it's in the runtime, which saves the goroutine's full CPU state where the garbage collector can find it, and calls into the goroutine scheduler. This actually has just a whiff of forward simulation in that we're redirecting the goroutine's control flow, but this doesn't require any single stepping in order to first reach the back edge. Once we had done all this work, there was one final step I haven't mentioned so far. We had to debug the Linux kernel. It turns out that when a new thread, which the Go runtime creates regularly, using an alternate signal stack, which we use in Go because goroutine stacks are too small to receive signals on, receives its first signal, like say, I don't know, a preemption signal. While there was a lot of CPU activity, which Go programs happen to be great at creating, on a Linux 5.2 kernel compiled with GCC 9, which introduced more aggressive common sub-expression elimination, the kernel could corrupt the SSE registers, which Go uses when copying and clearing memory, leading to memory corruption. To Linux's credit, this was fixed pretty quickly. Ironically, this actually came down to a bad preemption point in the Linux kernel, not between goroutines being scheduled onto threads by Go, but between threads being scheduled onto CPUs by the operating system kernel. It really is turtles all the way down. I want to wrap up by taking a step back and looking at the design space we explored. I said earlier that precise stack scanning meant we couldn't just preempt anywhere. But there are two sides to this equation. Most languages focus on the left side and drop the right side. That requires stack maps at preemption points and leads you down the path to back-edge preemption, which we saw was costly for Go, or forward simulation, which we saw had other issues. We ultimately took the other path. This led us to conservative garbage collection techniques, which don't require stack maps and enable zero-cost signal-based preemption. And this was only possible because Go, rather unusually, has a non-moving garbage collector, which gave us the freedom to use conservative garbage collection techniques rather than being forced into precise techniques. As often happens with Go, we wound up in a really unique point in the design space, but one that works well for Go. We took a long and windy road to get here, but in the end, we were able to combine ideas from languages, operating systems, and other garbage collection techniques to find a solution that works well for Go. This asynchronous preemption support finally eliminates difficult-to-diagnose, long-tail, latency, throughput, and stability issues caused by often invisible tight loops, and means that you all can write clear, parallel Go code without having to deal with the potentially adverse effects of some hidden loop. And to bring this all back to where I started, I finally get to rest for a while in my 5-year quest for microsecond scale stop-the-world garbage collection latency. Finally, I wanted to thank our awesome runtime and compiler team, especially Cherry Zhang and David Chase, who did a lot of the work that I showed you today, and without whom this simply wouldn't have happened. Thank you.